Hello, and welcome back to Stat 3050 at the University of Wyoming. We are indoors, but still having a good time, I think. I hope, at least. Okay, so today I've got a quick example in something a little new, still sort of the same idea, except we've got some categorical predictors instead of just the simple kind of continuous stuff. These categorical predictors are only going to have two levels, meaning that there's only going to be two different things within each predictor column. Okay, so what do I mean by that? Well, let's go over these goals and you'll sort of get a better idea. The first one being sort of what I was just saying, introducing categorical variables with two levels. So that's kind of that binary predictor, so like male versus female, with or without a disease, right? So just two levels, two unique indicators there. And then we're also going to use ggplot to sort of differentiate between the categorical predictors and how they may or may not be related to Y, or our outcome. And then sort of looking at reference levels when we're building models, we're going to be doing just a tiny bit of math, nothing too crazy, and I'll even bring out the whiteboard for that. And then using that best subset that we saw last week for these models, we're just going to have categorical predictors instead. Cool. All right. Per usual, this example is brought to you by I don't know why, but I've been thinking about Little Bear for forever now. Little Bear, I grew up watching that. I don't know if you have seen Little Bear, but I remember the music just being so good. If you go onto Spotify and just look up Little Bear soundtrack, you'll be in for a treat. It's just so nice, so nice. And then Over the Garden Wall, it's a little bit newer. I think 2014 is when that came out, but very similar vibe, both in the artwork and the music. Very similar. You should check it out. Little Bear is for kids, for children. Over the Garden Wall, I think also is for children, but I watched it and it's kind of spooky. So you should check it out too. It's real nice. It's a good time. Okay. Anyway, enough about the cartoons. Let's go into R. Okay. Okay, so we're in R, which is great. Let me make some more room here. Okay, and so what I want to do, per usual, set the working directory. I've got it so I've made a new folder called Categorical in my multiple regression folder there. This is not like categorical analysis or anything. We just have categorical predictors now. There's a whole class on categorical data analysis. But for now, we're just looking at the predictor side of things. So I've got that. And then the data that we're going to be working with it's pretty interesting. I think it's centered around lung capacity in humans. And we've got a couple of predictors that are I think pretty interesting. So let's go ahead and read it in. I'm going to call it lung. And then this one's a little different. So I got this data online. You can search for it if you're in the 3050 class. You should already have this available to you. But it's not a CSV file. It's actually a text file. And I didn't want to go and kind of switch that around because we can use this read.table. To read in text files. So same idea, just with a different type of file. So we've got that all set and ready to go. The data is called, I think it's called lungcapdata.txt. And if we read that in, oh yeah, nice. Let's take a look. Well, what happened? Uh-oh. In this case, it's necessary to put header equals true, right? When we're reading it in there on line 1 because, well, it's not realizing that the first row is actually the column names. And then it's sort of try to figure out the column names here too. Another thing that's interesting, we want to make sure that all of these data are being treated as the type of variable that they are. So these are all numeric, this is an integer, and these are all factors here. But if we just kind of hover over the column, it'll say column 6 or whatever, and it'll say factor with 3 levels. But if we look at it, it's only yes and no, but then it's including this Caesarean as another factor, which we don't want, right? And so that's kind of saying the same thing. If we look on column 3 here, the first thing in here is height, right? That's the column name. But since there is at least one cell in here with text in it, it's going to treat the whole column as a factor. So this says factor with 1 levels. Kind of funny. But that's that is not what we want. Let's go ahead and fix that real quick. We're just going to do header equals true. And we run that, and we'll see now, much better, right? Way better. So let's go over these data to kind of get an idea of what's going on. So the first column here, this is going to be our outcome. This lung cap is just lung capacity. And then we've got age, so that's an integer, I believe from like 5 to 19 or something like that. So that's good. And then height, this is a numeric, and then we've got 3 categorical predictors here. Whether or not you smoke, well, not you, but the people in this study, whether or not one smokes, and then whether they are male or female, and then, okay, so this is something that needs some clarifying. Caesarean here, or C-section for short, this is not whether you've had a Caesarean section or a C-section. This is actually if you were born via C-section. So, because you'll notice in here that there's a few males that say yes. Of course, you can't have a Caesarean section if you are male. So this is whether or not you were born that way. Okay. So we've got all that. That makes sense. That's all good. So let's take another closer look. Since we're working with these categorical predictors here, things work about the same way, but with a couple of slight differences. So the first thing we'll do is we'll run this summary on the data set, and let's see what we get. Cool. So we're used to seeing this, right? We kind of get the 6-number summary with the median and the mean for all of the continuous variables, but then we get these sort of kind of counts of the other data, right? The categorical predictors. So we see here that there's 648 people that don't smoke in the study, and then 77 who do. And then same thing, it's about half and half, males and females for that one predictor. And then let's see, 561 people were not born via C-section, and 164 were. So that's all you'll get for categorical predictors. Really, that's all you need. Just the counts, just so you can kind of get an idea. There are some rules with categorical predictors that are, more or less kind of liberal. But you want to have at least, 10 of each level that you have. And so we only have 2 levels in each of these. And by level, I mean 2 unique indicators in here. You want to have at least 10. That's not necessarily, the most stringent rule. But we see here that we've got plenty, right? It would be an issue, if you only had one person in here who smoked, or vice versa. It would be an issue if you had, 1 or 2 males and then the rest were female, or whatever. So just kind of keeping that in mind, more or less a double check than anything else. So that's all good. That's pretty easy. The next thing we want to do, and I've mentioned this a little bit earlier, that we want to make sure, now more than ever, that our factors are being treated as factors, or the categorical predictors are being treated as such, and then that the numeric variables are still numeric, okay? So we run this str, the structure, just so we know. And what do we see? Okay, so we've got the lung capacity is a number, right? So it's got those decimal points. The age is an integer, right? So it's just sort of rounded off. And then same thing for height. It's numeric. It's got decimal points. So that's all good. And then, good. So our 3 predictors here, our 3 categorical predictors, are being treated as factors with 2 levels. And then it'll print out the 2 levels, no and yes, female and male, no and yes. And then it'll sort of give, thankfully we don't have to do this by hand, but the computer will sort of give indicators for each, numeric indicators for each level there. So that's good. We'll come back to that in just a little second. Nothing too crazy here, so that's good. And also just a note, and we'll get into it again in a second. You can change these indicators from 1 to 2 to 0 to 1 or something like that. Of course, not important. Really, really not important. Ours is its default. Most of the time, defaults you can trust. Sometimes you may want to change it, but this is one of those cases where having this as the default is fine. Cool. All right, what do we want to do next? Well, let's just plot and see what's going on. So the point of this study was to see how lung capacity is affected by these 5 predictors. But what the biggest question is how does age affect lung capacity? And then these are more or less kind of secondary variables, not secondary in importance, not secondary in importance, but more or less sort of the question being asked. Okay, so how do we plot this? Well, we'll just bring in the old tidyverse that we're used to seeing, and we'll make it a scatter plot, right? We're pretty used to making scatter plots too. So ggplot, the data is going to be lung, and then the aesthetic is going to be age is our predictor in this case, and then y is our outcome, which is going to be lung cap. If I run that, totally blank per usual, but it's good to see just to make sure that we've got everything there and everything is being mapped out correctly. And then we'll just do the geome, the geome point, and then the geome smooth, and then per usual. I'm not even going to look at the lowest line because I don't really care. I already kind of have an idea of how this is going to go, but just always a good idea to put that LM in there. All right, so we run that. And we'll zoom it in. Whoa, nice. Look at that. Okay, so a few notes. The first thing is that it's okay that these points are all stacked up on top of each other. The reason it's doing that is because we don't have any decimal points for the age. They're all rounded up or down. So that's fine. There's really no big issue there. It looks funky, but it's totally legit and not an issue, okay? And then we see it's like a pretty clear straight line, nothing too crazy. The confidence band for the regression line is pretty small, so that's good. Not that a large band is an issue, but we're fairly certain that the line is somewhere within here. So that's good. That's all right. And we don't see any huge outliers either. So what do I want to do next? Well, let's just go ahead and make a model and just sort of see what happens. So that's just going to be, I'm going to call this just model. I'll call it model 1 actually, because we are going to be making a few. And that's going to get a linear model, and the formula is going to be what we have up here on 14 and 15, lines 14 and 15, lung cap as a function of age. And then the data, of course, is the data lung. All right, so that's good. And we'll hit it with the summary.lm and get that. All right, here we'll zoom that in. We see something pretty similar to the scatter plot. In fact, if we were to take this residuals versus fit and then kind of put it up next to the scatter plot, it would be just about the same, except this is now flattened, whereas the regression line kind of goes diagonal towards everything. But that's all fine. That's all good. So what are we looking for? Well, we're trying to make sure that the data fit around a line. We saw that in the scatter plot, it's pretty good. And we see that being mirrored here. Okay, and then we look at the equal scatter, right? We're making sure that all of the residuals aren't being clumped. There's no sort of fanning outward or fanning inward or any weird sort of unequal scatter going on. And I think that this is fairly decent. This is pretty good, right? Everything is pretty consistent throughout. If we were to divide these into equally sized bins and kind of count each dot, or at least eyeball, each point up here, we would get a pretty similar number in each bin. So that's good. And then we want to look at the distribution, okay? So we can look at the QQ plot, and we see here that everything is fairly decent. Maybe a little bit of going on over here and here, but that's like totally fine. So that's all good. Let's look at the histogram too. Same thing as a QQ plot, but I think that you can see the shape a little bit better because we're looking for a normal distribution, right? Or something that resembles a normal distribution. So we'll plot the histogram, we'll plot the residuals of the histogram, the residuals of the model here, and then we'll run that, and let's zoom it in. Whoa! That is about as normal as it gets. Look at that. Centered right there at 0, and like pretty symmetric on both ends, right? That's pretty wild. So actually, I kind of want to see what the summary of this thing looks like. So this summary function, when you just put in like a one-dimensional object, it'll give you the min, the max, the quartiles, and the mean. So we do that. Whoa! And the median too. Look at that. So the min and the max are, get out of there. The min and the max are sort of what we saw in the model output. And the quartiles are the same too. But look at the mean. The mean is 0. That's wild. That's really something. This is not totally necessary to do every time, but this is pretty curious, I think. So that's cool. That's neat. All right. Okay. Well, what are we doing next? Okay. Well, so the question was, how do these categorical predictors influence Y? So to get a better idea, we can actually plot a few categorical predictors at the same time on a scatter plot. How do we do that? Well, let's go back to the GG plot. And actually what I'm going to do, I'm just going to copy and paste. Because I don't want to have to type all that again. All right, so how do we do that? Let me kind of clean up the background here. And if I run that, we'll just have it up so we can see. I'm not going to zoom it in. But right now, this is not including any categorical predictors. This is only age, a continuous variable, and lung capacity, right, our outcome. So we have a few options in sort of, we have a few stylistic options with this plot. The first, and I think the most common way of doing it, is drawing two regression lines with different colors indicating the categorical predictor. Let's start off with smoke. Okay, so whether or not you smoke is a yes or no kind of thing. So how do we do that? Well, we'll just put in the aesthetic. This is very important. Within the aesthetic, because this will change everything. This will change the points and the smooth, right? Kind of global. We're just going to put the COL, and that's going to equal, you guessed it, smoke, right? That's going to equal one of our categorical predictors, smoke here. And if I run that, I don't need to change anything else. All I need to do is put in that extra aesthetic, and it'll map it appropriately. So we run that, and let's zoom it in. Whoa, look at that. So it's changed both the points and the line, right? So the color scheme here, for those who are interested or curious, is colorblind friendly. And that's the default by ggplot, which is pretty nice, I think. Very considerate. Let me get the mouse out of here too. But it was developed and sort of thought up by Cynthia Brewer, who I put at the very front of the syllabus, sort of a modern day statistician. She actually works in geography, making maps and stuff. But she was like a consultant on all of the aesthetic parts of these plots, sort of in the base code, which is pretty cool. So by default, it should be colorblind friendly, and you can go on to the internet and look up. There are more packages and more color options that you can use to sort of edit these based on if you're colorblind, stuff that's friendly for the printer, et cetera, et cetera. So that's pretty cool. Anyway, what do we see here? Well, we see now two lines two different colors and two different colored points too. We see that there's a few things to note. That the people who answered no, if they smoke or not, people who said no, they don't smoke, that is included in the whole range of data, right? Every age answered no, okay? But strangely enough, only I think 10 to 19 said that they smoked, right? So this brings up a kind of an interesting thing in that we have this rule where we can't extrapolate beyond the range of the data that we have. And now we sort of have more or less like a subset of data that we can't really extrapolate, right? And what do I mean by that? Well, if let's say that you're trying to predict a new value and you're trying to say, okay, this person is like 5 years old, trying to figure out their lung capacity, and they smoke. Well, one, wow, kind of sucks that a 5-year-old is smoking, but whatever. And then two, we wouldn't really be able to do that because we don't have data for lung capacity given that they're 5 and smoke, right? So just sort of keeping that in mind, that we're only really able to say, okay, from ages 10 to 19, we can, sort of predict both, right? Whether or not both, sorry. We can predict their lung capacity if they do smoke or not, right? So that's just one thing to note and kind of keep in mind. There's another thing too, is there's not that many overall people that smoked in this study. Still enough to be legitimate. And we'll make a model here in a second. But just notice that the confidence band for that blue line there, those are the people that smoke, is kind of wider than the confidence band is for the people who don't smoke, right? Because we have a lot more data on folks who don't smoke than do. And so sort of the last thing to note here too, which we know this now, but maybe 70 years ago or 60 years ago was not common sense, I guess. But we know that smoking is not great for really overall health, but definitely not good for the lungs. And we know that lung capacity intuitively should be decreased if you smoke. And we see that here. We see exactly that, right? People who do not smoke have a higher lung capacity than people who do. And we see that because the red line for people who don't smoke is over the blue line for people who do. So we can actually visually see that, which is pretty sweet, I think. So let's go back to the code. And let's say that you show this to your advisor or your boss, whoever, and they're like, okay, cool, I like the way that looks, except the red and blue dots, it's a bit much, okay? And you say, okay, that's fine. I'll keep the two lines, the two different colored lines, but I'll get rid of the colored dots and just make them all black, and then have the two different lines. How do we do that? Well, we'll just take out that color aesthetic from the global option, this foundation here, and we'll just put it in the geom smooth. So the first thing we need to do, since it's an aesthetic change, we need to say, actually map a different aesthetic for this one specific component of the plot. And it's going to be the same thing. It's just going to be within the geom smooth. So aesthetic first. If you just do the color equals smoke without the aesthetic, it won't work. Okay, so we'll run that. We'll zoom it in again. And now we see that all the points now are black, but we still have the two differently colored lines, which is nice, I think. So that's all good. That's fine. How about we add something else? We've got two other data points here, two other predictors, gender and whether or not you were born via C-section. Oh man, let's do gender next, and we'll not worry about C-section for now, as far as plotting goes. But how do I add that? Okay, well, same deal. So except we have a color option already kind of taken up. If I put, let's see, we're about to make like a rainbow here. So if I put aesthetic in the geom point and then maybe another color into the, let's see, into the aesthetic option of the geom point. Let's see what happens there. Whoa. Zoom it in. Okay, what happened? What happened? Nothing good, right? Nothing really helpful. Because now all of the colors are different, and the legend here says that all of these are gender, right? Female, male, no, and yes. Not helpful, because we know that no and the yes goes to the smoking predictor and not the gender here. So how do we fix that? Well, maybe instead of color, how about we make the aesthetic for the geom point for the gender? How about we make it shape? Shape. Interesting. What's that going to do? That's what that's going to do. So now we have circles and triangles and two different colors denoting whether or not you are male or female, and then whether or not you smoke. So this is all fine. We get into this idea, though, of making really busy plots. Okay, so depending on your purpose, it might make sense to do this. It might make sense to leave the dots alone and just have the two different colored lines. It might, be fine to have two different shaped lines, so you can make the lines actually dashed or dots or whatever instead of these colors. You have so many options as to how you make the plots look. But just like overfitting a model, right, adding a bunch of different predictors and stuff and interactions and whatever else, transformations, blah, 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 you can do the same with a plot, right? You can make a plot so busy that you have no clue what's going on. You have no idea. So maybe I just want to, I'm just going to get rid of this, and I'm going to be okay with the way that it looks now, right? So two different colored lines, and then we'll just leave males and females out of it. We do have plenty of options, though, with sort of making figures look decent and whatever else. But for now, we'll say this is fine, right? We get a pretty decent idea of how smoking affects lung capacity. But what we haven't seen yet are the actual details behind that. So how do we do that? Just asking all these great questions all the time. We'll make a model. We'll make a regression model out of it, a multiple regression model. So we'll call it Model 2. I hope you're keeping track of all these. And then it's going to get the same old, right? Formula, it's going to equal the outcome, so lung cap. Whoa, lung cap. Cap, not camp. And it's going to be as a function of age, and then, right, we just use this plus sign. We're not adding the variables together. We're just including another one in. Smoke. The data is going to be lung. Okay. We hit it with that summary.lm, model 2. We'll do that. Okay, so here we are. What do we see? Same old, right? We get the call, we get the residuals, and then the coefficients table. Okay, so this is a big deal, and I'm actually going to bring up the whiteboard here in a second to kind of help show how this categorical predictor is now included. But we see the intercept, so that's statistically significant right now before checking the residuals. Age, that's also significant, and then this new predictor, this new categorical predictor, is also statistically significant. So that's all good. And we see that we get a decent R squared, and the model p-value is solid. So this all is fine. We're used to seeing this, right? So for every 1 unit increase in age, lung capacity increases by 0.55. So how do we interpret this? Well, notice that the sort of output here says smoke and then yes. Smoke and then yes. So that's saying that yes here, this is yes and not smock eyes. No, this is just yes. This is saying, okay, with reference to yes, this is now the slope. Okay? This is how it changes the overall outcome on average. So let me actually bring out the old Microsoft Paint here, which I didn't know I had. I thought that this was gone. Crazy. Absolutely wild. All right. So here we are. So LC, I've sort of shorthanded it over here. Whoa. Like that. Okay. So that's all good. That's all fine. So as far as this part goes, we're pretty used to seeing this, right? This is all numeric. So this age right here gets the normal kind of continuous value. We can put in whatever we want so long it's within the range of the data. And then we just multiply that by 0.55, add it to 1.08, and then we've got lung capacity. But now that we have this thing in here, changes it just a little bit. So recall, and let me go back to the old output here, we've got smoke, yes, right? So it's treating yes as the reference level, okay? So it's saying, okay, based on the yeses, this is now the coefficient, right? That's the reference level. And how do we include that into our model, though, into at least the interpretation? Well, great question. So if smoking here is yes, that's just going to get the value of 1, okay? And 1 times anything is whatever you're multiplying it by, right? So in this case, it's negative 0.64, right? So when that's included in the model, when that smoke, if they answered yes, when smoke equals yes, you can just plug in a 1 there and then take whatever value this is and then add it, or in this case, subtract it to the intercept, right? So when they smoke, lung capacity, and I'm going to kind of shorthand under here, when they smoke, right, is going to be 0.44. That's 1.08 minus 0.64 plus 0.55. Age. Okay. So we see that when smoking is included, it on average brings down lung capacity by 0.64, and then it gives you this new regression equation, this 0.44 plus 0.55 age times age. Okay, so that's all fine. If they don't smoke, then we just take our regular regression equation. I'm going to say no smoke. We get our we get our regular regression equation of 1.08 plus 0.55, because what we've done here now, and I'll give us some more room, is that, well, let's see, the coefficient is negative 0.64. And since they don't smoke, we just multiply this by 0, because our reference level is that they do smoke, is yes, right? And we know that 0 times anything is 0, so that's all gone. And then we're just left with this regression equation. Oops, I forgot age there, but it's there, okay? So you just plug in age, 0 for smoke, right, if they don't smoke, and then you're set. So you essentially get 2 different equations, right? You get one that has the reference level, so 1, right? And then you get a slightly different intercept, right? Just slightly, is because you're now adding in that constant when it equals 1, that predictor, that categorical predictor equals 1, then you just add that to the intercept, and then you get your new equation. And then when they don't smoke, you just leave it out, and you're left with the same thing, right? So that's all fine. That's all good. So we say here that on average, smoking decreases your lung capacity by 0.64 on average. Okay, so that's all fine. That's all good. So we're back in R. This is all good. You can see my math here. Okay, so what do we do next? Well, I think I said I wanted to do that best subsets thing. Let's go ahead and include all of the variables, right? Let's go ahead and do that. And then we'll do some big time interpretation. And then we'll use that best subsets, and then we'll be out. Okay. So we'll call this model 3, and it's going to get formula equals lung cap as a function of everything else that's not lung cap, which is just going to be denoted by that period here. And then the data is going to be lung. Hit it with that summary.lm, model 3. What do we get? Whoa, significant everything. We haven't checked the residuals. We will in a little bit. But now we see that, okay, including all of this, we've got age and height, right? So that's all fine. And then we've got our 3 categorical predictors, okay? We've got smoke with the reference to yes, right? We've got gender with a reference to male. And we've got cesarean with a reference to yes, okay? So that's just by default. There are ways that you could go into R and change that yourself, but we'll just leave it for now. I'm not going to be too worried about that. But we see here for every 1 unit increase in age, lung capacity goes up by 0.16. And then for every 1 unit increase in height, lung capacity goes up by 0.26, okay, on average. And then we saw earlier, the coefficient has changed just a little bit because we've included now more things, right? We've included more things. So things are going to get, some variables don't have to do as much work now since we've got other variables kind of carrying more of the load there. Okay, so anyway, so smoking, when smoking equals yes, on average, lung capacity will decrease by 0.6, right? And then if they're male, on average, and this is all holding the others constant, right? This is not sort of including one or whatever. This is holding everything else constant, right? When gender equals male, lung capacity on average increases by 0.38, okay? And then when holding all others constant, you'll hear me say that all the time, but when people who were born via cesarean or C-section, their lung capacity goes down by 0.21 on average. Okay, with p-values all backing that up. This is a little bit of not as much evidence, but still below 0.05, so that's fine. And then R squared is fairly decent. The adjusted R squared is not much different from the overall R squared. So that's a good indicator that everything here is fine. We're not overfitting the model. And let's just go ahead and check the residuals too. So we'll do that real quick. We'll do the auto plot. And then the object is the model 3. The smooth color is NA. And then the background is out of here. All right. So I am straight up losing my mind. Okay. So the residuals look pretty decent, right? Nothing too crazy as far as curvature. Equal scatter is pretty much here. It's a little bit unequal out here, but honestly, like, I think it's fine. If somebody had an issue with this, then they're being super, super strict. But you can reassure them that it's fine, because when we look at the histogram in this QQ plot, everything is fairly decent. We've got a really big sample size. So that's good, right? So we'll go ahead and check the histogram real quick of the residuals. Run that. Whoa! It's pretty decent again, right? I'll check the summary again because I'm kind of interested in what the mean is, but it's certainly going to be super close to 0 here, right? But this histogram looks really good. This histogram is about as normal as it gets. Let's go ahead also, let's just check the summary of the residuals because I'm just interested. The mean, again, is 0, right? Median is a little bit bigger, but that's fine. And everything here is fairly symmetric. We see that in the histogram. We saw that in the QQ plot. I think everything here is good, right? So let me give myself some more room here. And let's do this best subsets thing. So I'm going to call this, per usual, best subs. No, wait. First, I'm going to load in the leaps package. Sorry. And then I'm going to call this best subs, and it's going to get, remember the function, it's called reg subsets. I almost forgot. Reg subsets. And then remember, you don't have to put the formula equals. You can just put in the formula, which is lung cap as a function of everything. And the data is going to be lung. Now, before we run that, I'm kind of interested in sort of the top maybe 3 best subsets of variables, okay, for each subset size. So I'm going to use this n best, and I want to do 3. And when I run that, it's going to take just a second. Gosh, just moments. Crazy. The math behind this is actually pretty intense, and I think the computer doing it so quickly is pretty cool. Anyway, and then, sorry. So then we'll load in the, let's see, the cars package. Cars? Car, not cars. Okay, and then we'll do the plot of the best subsets, right? How do I do that? Well, great question. We use that subsets function, not subset. And it's going to be, the object here is going to be best underscore subs. And then the other one, here it is, the statistic. What do we want to do it by? Just a great question. We could do it by BIC. I'm more curious in the R squared for this, the adjusted R squared. So we'll just do ADJ RSQ2. Is that it? No, it's ADJR2. It's okay to keep mistakes in. Cool. All right, so already this is going to be kind of clumped because of a few things. First thing is because the R squared adjusted here it's 0.8, so that's pretty all right. And also we've included the top 3 out of the top 3 variables for each subset size. Okay. So for right now, let's just look over here at subset size 1, just so we can see what's going on. We see here that if we just wanted to include one variable, the best variable to include is height. And then after that, it's age. And then way after that, it's just modeling if they're male or not. That R squared is almost 0. It's so small. But we see that height, including height, height's doing a lot of work here. But when we include height, it brings that R squared way up. Okay. So let's zoom it in so we can see kind of the other options here. So that's just going to be this wide lim. And since this is a base R function, that's going to take 2 values. The first one is going to be the lower, and the second one is going to be the upper bound. And since I got to zoom this back in just to kind of see, I think 0.8 is the lowest. We'll do 0.8 to 0.85 and see where that gets us. So 0.8 to 0.85, got that. Oh yeah, no, bad. We'll do 0.89. Oh yeah, we'll put this up here. Cool. Zoom that in. And what do we get? Age is cut off, but that's fine. So we see here that for subset size 2, the best combination of variables is age and then height. And then after that, the second best combination is height and then smoking, and then height and then gender. Age and height is pretty similar to the next subset, the next best subset in the next subset size, which is age, height, and then it's kind of hard to tell, I know, but that's an S and a G on top of each other. So that's saying that age, height, and gender, and then age, height, and smoking are both doing about the same. However, we get more meaning, I think, out of the smoking, right? Okay. We get more meaning out of the smoking because smoking is something that is known to be destructive, right? Especially on the lung, on the respiratory system. So I would be convinced to keep that in there, to always have smoking as a variable in there, rather than whatever the computer says is actually the best. So we can move on to the other subset sizes, but we see here that they're all just about the same, with the only difference being maybe a % difference, and that's just being so picky, so picky. So what I didn't do in the last video, and I meant to, is remodeling things. So I'm a big fan of having age, height, and smoking as the 3 predictors, the quote-unquote best for that subset size. So let's go ahead and do that. Age, height, and smoking. I gotta remember that. So formula equals lung cap as a function of age plus height plus smoke. Cool. And then the data equals lung. So we got that. And then summary.lm, model 4. Give us some more room here. All right. Cool. So we'll ignore the residuals because we already know they look pretty decent. And then the coefficient table. So for every 1 unit increase in age, lung capacity increases by 0.13. Makes sense. Height, same deal, right? Every 1 unit increase in height results in a, on average, 0.278 increase in lung capacity, holding all the others constant. And then if you smoke, it's going to bring down the average by 0.648, 0.649, or whatever. Same deal. We get now we can actually see the R squared here. It's 0.84. If you were curious to see the R squared, you can just make a model out of each of the best, the top 3 or whatever for the subset size, and you can see how they differ. Honestly, it's like by, I think, 1%, so it's not that big of a deal. I get more meaning out of having smoking in there rather than everything else. But, whatever. So this is all good. We'll just look at the residuals real quick. And I'm not even going to make it look pretty because I already know that it's going to be fine. So I'm just running autoplot with model 4 in there. And then we see here that it's decent, right? This line says there's some curvature, but honestly, there really isn't. I don't think that's totally the best picture or whatever. But we see here that it's all fairly consistent. Equal scatter. First assumption, goodness of fit. It's all fitting around the line. There's no curvature. There's equal scatter, and then the distribution I know is going to look normal. Based on the QQ plot here, I could plot the histogram if I wanted. I'm not, because we've got a lot of evidence already that the histogram is decent. Oh, boy. All right. I know I've been talking a long time about lung capacity and smoking, but one last thing I want to do, is I'm going to make one more model, and it's going to be just smoking. So it's going to be formula, it's going to equal lung cap as a function of smoke. And that's going to be data equals lung, summary.lm, model 5. Good Lord. Oh, boy. All right. So what does this say? We see, well, this is interesting, right? We're now seeing that the interpretation here is that with the intercept included, as if smoking equals yes, right? If smoking essentially equals 1, right? Yes equals 1, then lung capacity goes up by 0.87. And if they don't, then lung capacity on average is just 0.7 or is 7.77. Okay. Does that make sense? Hell no, it doesn't. Of course it doesn't. We don't have a lot of information here. And take a look at the multiple R squared and the adjusted R squared. It's so low. It's so low. We would say here that, based on the adjusted R squared, which is the one that we should kind of always be looking at, we would say that 0.89% of the variance of y is explained by x, which in this case is nil. It's nada, right? So it's just not good, right? Let's also look at the residuals here. Again, not going to make them pretty or anything, because we would say here that there's just no equal scatter, right? Well, one, because they're all clumped up, right? This is all the zeros and this is all the ones, right? Essentially. What's the deal? Well, we have way more people that don't smoke than we do that do smoke, right? But what we would say here is that, hey, this is not good, right? This is not an adequate model because we're only including the one variable, right? And it's essentially just a 0 or a 1. So let's also just look at the histogram, and it might look okay which in this case it kind of does, but it's a little bit more left skewed than it normally was in the other models we saw. But we don't care what this really looks like, because this right here ain't good, right? It just ain't good. So why am I showing you this? Well, great question. Just a great question. Let's make an ANOVA. Do you remember that? Remember how we did ANOVA all those months ago? Well, let's do it again, but let's do it on these data just with smoking. Okay. So I'm just gonna call it ANOVA. It's gonna be the same. Instead of LM, it's gonna be AOV, but the formula is still lung cap as a function of smoke. The data is gonna be lung summary.AOV. Let's see. Whoa. Whoa. All right. What do we see here? Ignore my my little mistake. We see whatever we get. Blah 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 blah. Remember that the question that ANOVA answers is there a difference between the two levels that we're looking at, or the however many levels we're looking at? Which in this case we would say that yes, there is a difference. What is the difference? Well, we don't know yet. But we would say that there is a difference because it's 0.0063 here. It's way below 0.05. We would look at so it's 0.063. Where have we seen that before? Whoa. It's the same. It's the same p-value in our linear regression model here, just in a different kind of context, right? So that's interesting. Let's look at the old residuals too of this thing. All right, zoom that in. What do we see? Oh my Lord. It's the same thing. It's the same thing, right? Very interesting. Very interesting. What is the difference? Well, what we could do, we have a couple of options, but let's just do this Tukey HSD, because I'm a fan of that. Tukey is pretty moderate, so we run that. And what do we see here? P-value of 0.0063, right? And then a difference, on average, of 0.87. So yes minus no. 0.87. Where have we seen that before? Whoa! It's the coefficient. It's the coefficient for this estimate, for smoking. Very interesting. Very interesting. What am I saying here? Well, what I'm saying is that ANOVA and a linear regression, when you just have the one predictor, it's doing the same thing. It's doing the exact same thing. Okay. So then, what else can I do? Just to show you that so many tools in statistics kind of do the same thing, just in different methods. Let's do a t-test between yes and no, and the lung capacity. How do we do that? Instead of moving things around and stuff, what I am going to do, I'm just going to use this pairwise t-test, and we'll use that same notation that we're used to seeing in the t-test world, where it's x is going to be the continuous variable, this lung cap, and then g. G is going to be lung cap, lung, and then, let's see, smoke, right? So x is just the continuous, g is the group, and then it doesn't matter since we have only two levels within the column, right? That one factor. So it doesn't actually matter, but I'm just going to put none for the adjustment method, just in case, because this is more or less just showing you, just as an example. Here we are. Okay, so what do we get? A p-value of 0.063. Wait a second. 0.0063. Whoa, wait a second. 0.0063. Okay. 0.0063. And you guessed it, 0.0063 for the regression, right? So the regression, the ANOVA, this t-test, doing the same dang thing, which is wild, I think it's so crazy. I'm getting a kick out of this, right? So as we include more variables, things change, right? And another thing, just before I forget. Oh, you're going to hate me. When we go into the ANOVA, we can actually pull out the coefficients, right? And notice 0.77 plus 0.87. If we come back up here to the regression, in fact, let me just do this. Good Lord. Run that, and then the model, I think it's 5 coefficients. Whoa, it's the same thing. Oh my Lord. So I hope that you're getting as much entertainment just listening to me laugh to myself than as I am doing this. Anyway, so it's all the same, right? It's all doing the dang same thing, which is pretty crazy. Which is just pretty crazy. So that's it for now. So I'm going to move on. The next example will be on predictors, categorical predictors with more than 2 levels. So 3, 4, 5, however many. Things change just a little bit, but it's still the same kind of situation, you know. So with that all being said, I will see ya next time.